So for number 12, a 1.5 kilogram block at rest on a tabletop is attached to a horizontal spring having constant 19.6 Newton per meter, as in the figure. The spring is initially unstretched. A constant 20 Newton horizontal force is applied to the object, causing the spring to stretch. For part A, determine the speed of the block after it has moved 0.3 meters from equilibrium if the surface between the block and tabletop is frictionless. For part B, answer part A if the coefficient of kinetic friction between block and tabletop is 0.2. So this is the spring in equilibrium, and then this is it after it's been stretched 0.3 meters by this 20 Newton horizontal force. So for part A, we want to find the velocity after it's been stretched 0.3 meters. So the initial energy is going to equal the final energy if we include this 20 Newton force in our system. So then we're going to put the work done by that applied force on the initial side. So we're going to, and then set that equal to the final kinetic energy plus the final potential energy of the spring. So 20 newtons times 0.3 meters equals 1/2 mv final squared plus 1/2 kx squared. Solve for v final and we'll get 2.61 meters per second. Now for part B, we want to find the final velocity after it's been stretched 0.3 meters, given that there is kinetic friction between the block and the tabletop. So these are all our forces acting on the block at this time. We have the force of the spring pulling this way, and then now we have friction pulling this way, and the applied force still pulling this way. So the initial energy is going to equal the final energy if we include the work applied and the force of friction and the work done by friction in our system. So once again, we're going to put the work done by the applied force on the initial side and set that equal to the final kinetic energy plus the final potential energy of the spring. And then we're going to add the absolute value of the work done by friction because the energy was technically lost by friction. So we're going to add that back in to our final energies to compensate. And in order to find the work done by friction, we need the normal force. And we can do this by summing up the forces in the y direction. So normal force minus weight equals 0. And then we get normal force equals 14.7 newtons. So we're going to plug in our force times the distance equals 1/2 mv squared plus 1/2 kx squared plus the absolute value of mu, which is 0.2, times the normal force times the distance, and we'll get velocity final equals 2.38 meters per second.